In question 3, we have a series of reactions where I've asked you to predict the major organic products for each reaction that's listed. And these should be the kinds of questions that you should get very used to answering, because from this point forward, through the rest of this course, as well as through the rest of Organic 2, you should expect that you'll see questions like this on every single exam. And so it's questions like this which are one of the reasons that I think the flashcard approach becomes very valuable and very useful, because you want to be able to look at these reactions and especially, see those reagents and say, oh, I know BH3THF followed by peroxide and base. That's a reaction that adds water to an alkene and does it in an anti-Markovnikov fashion. And so an anti-Markovnikov reaction, recall, is one that adds the hydrogen to the more substituted carbon and the other group, the X group, to the less substituted carbon. And so for the hydroboration of this compound here, we'd get the alcohol on the less substituted carbon, the hydrogen on the more substituted carbon. In part B, we're looking at osmium tetroxide and NMO. This is a reaction that forms diols, and specifically forms cis diols. So we know that the two carbons of the alkene, almost every reaction of alkenes, we lose the pi bond. The pi bond ends up functioning as a nucleophile or in some other way, but those electrons are almost never still there as an alkene. But what this reaction does is it adds a diol, and it adds them to the two carbons that were the alkene, and it adds them on the same side. Now, in a reaction like this, there's not going to be any preference for adding them both up or both down. I mean, in fact, in this molecule, those would be the same thing because these are not chiral. We have a internal plane of symmetry right there. But even if there was something that made the molecules chiral, it wouldn't matter if you added them on the same side. If you added them both up or both down. Without other reagents, there isn't a way to control or predict that. All right, part C is a hydrogenation, but it's not just any hydrogenation. It's using Lindlar's catalyst. And Lindlar's catalyst, you may recall, is palladium with barium sulfate and quinoline. And the purpose of those other reagents is to essentially poison the catalyst. We make them, we actually make it a worse catalyst. And in fact, Lindlar's catalyst ends up only being strong enough to react with alkynes. Recall that was the entire point of Lindlar's catalyst, is that we could do a hydrogenation of an alkyne and stop at an alkene, and the alkene won't react further. Since what we have here is an alkene, nothing will happen. Part D is our oxymercuration of an alkyne. Oxymercuration is another hydration type reaction that adds water across the alkyne. It adds to the more substituted carbon, which would technically be that one. It adds a hydrogen to the other carbon. But with these types of reactions, we're not done. This functionality here, which you should recall is known as an enol, under either acidic or basic conditions, will tautomerize to form the carbonyl. And so the final product of this reaction is this one here. Part E, we have the Simmons-Smith reaction. Simmons-Smith uses these reagents pictured here to form a cyclopropane ring. Um, it wouldn't matter which alkene you chose to use. You could use any of the 3 alkenes, but the product here is the cyclopropane ring. All right, part F, we have the addition of HBr. This is a Markovnikov process. So it adds the hydrogen to the less substituted carbon and the bromine to the more substituted carbon. But for this question, the 2 carbons here are equally substituted. They're both secondary. And so another way to think about a Markovnikov process is it adds to the most stable the bromine will add to the most stable carbocation. Well, if those are our 2 choices of carbocations, the bottom one, that carbocation is stabilized by resonance. The one on the right, this one is stabilized by resonance. This carbocation doesn't get any resonance stabilization from the aromatic ring. And so this is the more stable carbocation, and so that's where we find that the bromine will end up. In part G, we have a hydrogenation, but now with just our standard catalyst. And this is a catalyst that can hydrogenate both alkenes and alkynes. And in a molecule like this, we would expect that any alkenes or alkynes would all get completely hydrogenated to the alkane. And so that would be the expected product. The ring on the left, the aromatic ring, remember, those are not considered alkenes or alkynes. Those are a completely separate functional group. And so because of that, the aromatic ring itself doesn't get touched. In fact, if you want to hydrogenate an aromatic ring, you typically need about 130 atmospheres of pressure. In part H, MCPBA is the most common way that we make an epoxide from an alkene. In part I, we're attempting to add iodine to an alkyne. Now we said using bromine or chlorine is a great way to halogenate an alkene or an alkyne, but iodine, not really reactive enough, and this reaction just in general won't work. And then in part M, we're adding NaNH2, which is a strong base, strong enough in fact to deprotonate the alkyne, and then that terminal alkyne that's been deprotonated can do a substitution reaction, kicking out the iodine and giving us our alkylation reaction.